So as you can see here, I have a Department of Energy banner on my slides because I do this in connection with the US DOE, which is not the only, I'll say, organization in the world that's looking at technologies for recovering uranium from seawater. I will focus on activities in the US, which is, I'll say, the largest program in the world at the moment in this talk, but also discuss activities elsewhere in the world, too. That was clearly the wrong button. Try this one. Also the wrong button. I guess I'll use the keyboard. There we go. Okay, so why are we here talking about uranium recovery from seawater? Well, it's a very long-term question. As I'll get into shortly, the supply of uranium to power our reactor fleet today is secure and largely assured for the next several decades. So I'm here to talk to you today not about a technology that's transformative in the short term. Anyway, uranium resource costs are only a small part of the total cost of producing nuclear power at the moment, only around 5% or so. But really a technology that has a potential to be transformative in the long run under the circumstance that uranium resources may become scarce or difficult to obtain for other reasons in the future. So uranium recovery from seawater has been, I'll say, a technology that has been pursued for several decades now, beginning in the 1960s. And why has it not come to fruition yet? Why is it challenging? Well, the resource in seawater is vast, more than 4 billion metric tons, which is around 1,000 times of all of the conventional terrestrial uranium resources that we know about at the moment. And so essentially it's an unlimited resource of uranium, and it's one that is also recharged by natural mechanisms. So if we do extract uranium from the ocean, it's recharged by interchange with the seabed, it's recharged by runoff from fresh water. The challenge, of course, is the very low concentration of uranium from seawater, around 3 parts per billion. Conventional ores that are being mined today by conventional techniques or in situ leaching have on the order of 1,000 parts per million uranium. So this is several orders of magnitude lower in concentration. Therefore, whatever you do to recover uranium from the ocean has to recognize it has to be very energy efficient. It has to be very cheap, inexpensive material because you're recovering very little uranium per unit of material that you deploy. There's very little low concentration of it in the ocean. And that'll be a theme you see throughout this talk. Right? So the attractive aspect of this, since it does represent an essentially unlimited supply, is that if it's developed to the point where it can convincingly be established as a technology that will work, it will provide a price cap, or economists call it a backstop technology. In other words, the price of uranium can rise to a certain level and then no higher. The infinite resource becomes available and becomes competitive at that point. So that's one aspect of the appeal of this technology. Another, of course, is the security of supply. It's available to any country, essentially, with access to the world's oceans. Okay, so what am I going to be discussing today? Motivation, then why is it of interest in many countries to investigate technologies for recovering uranium from seawater? And I've already mentioned this idea of a backstop technology. And then background, what has been done from the 1960s to the present in the US as well as elsewhere. And then technology, I'll get into a little bit of chemistry here, a little bit of innovative design of mechanical systems, some being done here at MIT. To look at how to efficiently recover this material from the ocean. And then I'll talk about cost. There's a long history of cost analyses in parallel with the development of the technology and prospects for further evolving the technology toward viability. As well as I'll finish with obstacles to the development and deployment of the technology, of which there are several. Okay, so first of all, why uranium? Well, there are a handful of elements that it is feasible to recover from seawater. The plot that I'm showing here is a price on the vertical axis in dollars per kilogram versus concentration on the horizontal axis. And so the farther up and to the right you are on that plot, the higher the product of price times concentration is, and the more appealing that element is to recover from seawater. And so you see uranium, it lies, I'm drawing a diagonal line there, essentially of a line of constant price times concentration. There are only a couple of elements in the ocean that are more appealing by this metric than uranium, and both of those, are zirconium and magnesium, are of relatively low value. Right? So then the cost of hauling the materials becomes significant and really makes the technologies less appealing. So uranium on the frontier there, along with molybdenum, you see gold a little bit farther up, lower concentration but higher value, are all potentially appealing resources to recover from seawater. Vanadium is another one, not quite as appealing as uranium, but close, that you see there in the mix. Okay. So uranium is available as a potentially attractive supply from the oceans. Why has it not been pursued more aggressively so far? Well, in the near term, as many of us in this room know, uranium will remain a relatively inexpensive and plentiful element. And this plot here shows, going back to the mid-1960s when data really started to be collected in a systematic fashion, the data points show the estimated conventional uranium resource base, right, under the soil around the world. And the solid line shows the cumulative extraction of uranium from the Earth since detailed record keeping began in the mid-1960s. And so what you see here is that the resource base, the size of it, the blue dots, has risen from 3 million tons uranium to over 7 million tons, even as we've taken over 2 million tons out of the Earth. So essentially what that means is that discoveries have outpaced extraction to the tune of around 6 million tons over the past 50 years. And to put it in perspective, world annual consumption right now is around 60,000 tons per year. So essentially we have close to 100 years of supply, if you want to think about it that way. Of course, that number is very dynamic because assuredly we will continue to discover more uranium, right, from conventional sources. This really does only look at conventional sources. Looking forward into the farther future, and here I'm going to rely on the 2011 study produced here at MIT, The Future of the Nuclear Fuel Cycle, looking at projections of the evolution of the cost of producing uranium farther into the future. And what this plot is showing on the horizontal axis is cumulative production of nuclear power, which is proportional to cumulative use of uranium. And on the vertical axis is the cost of producing uranium normalized to a value of 1. The number is a little bit small there, right? 1 being the current cost. Right? And so what this manifold of curves show is a projection of the evolution of the cost of producing uranium over, I'll say, the next 100 years as a function of how much nuclear power is deployed. And really, as many of us know, there's a competition here between, well, you're, of course, extracting the most economically attractive resources first, and those are those nearest the surface, highest grade, and then moving to less attractive resources as the most attractive ones are depleted, and that tends to push production costs upward. But of course, we're continually discovering new types of deposits, new means for exploiting deposits that were previously uneconomic, and in situ leaching is a good example in the uranium industry, and generally becoming more efficient at extracting the commodity. So essentially what this manifold here shows is probabilities, right, that the uranium production cost will evolve along the lines shown there on that log-log scale. And so today's production cost, if the fleet continued to operate around the world at its current size for 100 years, versus a much larger nuclear fleet operating for 100 years. And the payoff there on the bottom, I've highlighted in blue, is, according to this estimate, around a 10% chance that uranium production costs would increase by more than a factor of 3. So then this is one way of thinking about the cost of producing uranium looking far into the future. So then getting back to the motivation for looking at uranium recovery from seawater, I try to convince you that in the short to medium term, the search for plentiful uranium from the oceans is not an imperative. It's not going to be a driver of decisions made between different nuclear fuel cycles, those that use uranium more efficiently than today versus today's once-through fuel cycle, or between nuclear and its competitors. Really, the objective we're looking at here is far in the future, thinking of investment in uranium recovery from seawater as a hedging strategy, one of several hedging strategies, right? Considering a possibility of unknown likelihood. I've given you MIT's efforts to understand what that likelihood might be, right? A possibility that uranium could become scarce and expensive in the future, right? And hedging against that in the nuclear industry has been kind of a theme throughout our field for several decades. Originally, back in the 1950s and 60s, the concept was that uranium would become scarce and expensive in the relatively near term, so it was an imperative to develop closed fuel cycles that used uranium very efficiently. right? And now our current understanding is that that imperative has moved off into the more distant future, but it's still out there. And so there's still this feeling of needing to have a set of technology options that represent hedges against that eventuality of expensive uranium. And really closing off that eventuality is of considerable value to decision makers looking at technology R&D, right? If we can say for certain that uranium prices will not exceed a certain value in the future because we have an essentially unlimited resource we can tap, that's worth billions of dollars of R&D that might have been directed towards technologies that we can say convincingly won't be needed on the grounds of resource scarcity. And now for the nuclear engineers in the audience, I'm not saying that closing the fuel cycle has no purpose or extending the efficiency of the use of the resource. Certainly there are waste management motivations that are very compelling to do so. But the resource motivation, which has often been advanced as an argument for closing the fuel cycle, may be in a red herring. And if we can close off that motivation by understanding uranium will assuredly remain plentiful and available, then that has quite a bit of value. So I want to wrap up the discussion of motivation and then move on to the background. What has been done over the past several decades, technologies for developing the recovery of uranium from seawater. This plot is fairly busy. It's a timeline presented in the context of historical estimates of the cost, inflation adjusted to year 2010 dollars, of producing uranium from seawater. And so as you can see, the consensus has been, and it hasn't changed a lot over several decades, that this cost would be, let's say, $500 to $1,000 or $1,500 per kilogram of uranium. Put that in perspective, current market prices are around $100 per kilogram uranium, as they've largely remained for the last several years. The variation there, I'll say earlier on, many of these cost estimates were more like wishful thinking or projections, assuming that a certain level of performance could be obtained by whatever material was adsorbing uranium, because there was little large-scale experimental work early on during this time period. But I'm going to use this plot to give you a narrative of how the thinking about how to efficiently extract uranium from seawater has evolved over the past several decades. So initially in the 1960s through 1980s, the adsorbent that was considered was hydrous titanium oxide. And I'm going to introduce a unit there that I'll discuss frequently, grams uranium per kilogram adsorbent. Right? And the hydrous titanium oxide was seen to be capable of recovering around 1/10 of a gram of uranium per kilogram of hydrous titanium oxide adsorbent. So basically 1 part in 10,000 by weight, right, and by mass. And the higher that number, obviously, the more appealing the adsorbent material. And you'll note that that number never really gets very high, right, because of the relatively low concentration of uranium in the oceans. The most that's been demonstrated so far by any material is only around a factor of 10 better, 10 to 50, in terms of grams uranium per kilogram of adsorbent. And so what that means is that this material that has to be put in the ocean, the material has to be cheap because you're only recovering a few grams of your product per kilogram of the material. So that rules out very exotic substrates unless you can demonstrate orders of magnitude enhancement in capacity, which is difficult to see equilibrium concentrations of orders of magnitude higher than what's been seen here. But anyway, let me continue with the narrative. Hydrous titanium oxide. Initially, many of the schemes, because of the low capacity of titanium oxide, involved active pumping of water through various mechanisms. I'll illustrate a couple of them a bit later on. Active pumping of water, especially if you're pumping to a reasonable head, is energy intensive, and you would require much, much higher adsorption capacities in order for that technology to be viable. You see some pretty high bars there, which I'd say were even optimistic assumptions. So a transition was made in the 1980s away from actively pumped technologies. And here MIT played a role again, I'll mention that momentarily, toward another adsorbent, the amidoxime ligand on an acrylic substrate. And the amidoxime has a capacity that's around an order of magnitude higher than the titanium oxide. You'll see the amidoxime persisting since the 1980s. And this is one of the holy grails in the field. Right? There has been a continued search for ligands more effective at grabbing uranium out of seawater than amidoxime, or than the acrylonitrile that is made from, or the amidoxime that's made from acrylonitrile and other chemicals. I'll talk about that momentarily. But so far that's been a chimera. We haven't found a better adsorbent than amidoxime. If we should do so, then this picture could change quickly and dramatically. Out of all the possibilities, I find it hard to believe that amidoxime is really the best ligand. But you have amidoxime and an acrylic substrate. Acrylic had a disadvantage at the time that it's relatively brittle and difficult to work with, not favorable for maritime environments. So then an innovation in the 1990s was to switch to a polyethylene substrate. This was an innovation primarily in Japan, which really enabled passive collection using essentially current motion, and the currents involved don't have to be a very high flow rate in order to get effective recovery of the uranium. And so then we advance by the beginning of this century to the kelp field concept that I'll show a little bit later, of essentially braids of the adsorbent, slightly positively buoyant, suspended upward from the seabed, which continues to be, I'll say, the reference concept for how to get this material physically out into the ocean to soak up uranium. So then let me go onward and go back to the 1960s through 80s and talk about what some of the early concepts looked like. So I mentioned many early concepts incorporated active water circulation, which was needed for the adsorbents that had relatively low uptake at the time. But it wasn't realized for, I'll say, longer than it should have been, that active circulation, unless you could recover essentially all of the uranium from the water you were circulating, which is impossible as it turns out, active circulation was simply too energy intensive to make sense. Other concepts a little bit later on, involving the acrylic substrate or other materials that took the form of beads or a slurry, right, had to be, their structural integrity had to be provided for them. So in the lower illustration there, you see a concept of adsorbent moored off of a ship, right, and there were concepts involving offshore platforms as well. Right, the problem is there as well, the mass of the structure that was holding the adsorbent, as well as the costs associated with hauling the adsorbent and all of its structure that's containing it in and out of the water, proved to be prohibitive. So all of these concepts really founded on being simply too energy intensive. Right. So an MIT hosted actually a large effort in the 1980s, the uranium recovery from seawater effort, which was the first to really focus in on amidoxime, and the first to propose the artificial kelp field strategy, later developed fully by the Japanese. It didn't work at the time that the MIT folks were looking at it because the acrylic was too brittle, and the idea of suspending this material essentially as standing kelp fronds in the ocean didn't work out with the acrylic substrate. Right? But later on it did. MIT conclusively shown that pumping was only feasible if uranium recovery was very efficient, because at, I'll say, the sort of moderate water velocity that most of the schemes were considering, each kilogram of water that you pumped, the amount of uranium contained in that water is $60 worth of uranium. And that cost turned out to be prohibitive in the context of the cost of pumping that amount of water. So to move onward then, the Japanese took built upon much of the work proposed at MIT, introduced the polyethylene substrate, and arrived at the standing kelp field scheme that you show here, where the illustration on the right shows the kelp braids moored to the bottom of the ocean. Here it's an RF system for releasing the adsorbent. Actually, the reference scheme these days, because the individual release mechanisms are a little bit too expensive to put down into the ocean and then only use once without recovery, the reference scheme really involves mooring the adsorbent in chains or other brackets on the seabed and then using ships to winch it up. Right? And on the left, you see the process for preparing the adsorbent. Well, how does this work? This is a nice illustration. The fundamental process is still the same, so I'll talk you through it here. You start with a trunk polymer, some base material. You use radiation to essentially open up grafting sites, radicals, right? Electron beam or gamma radiation. And then you graft a monomer, right? Acrylonitrile being one of them, onto these sites that have been opened up by the radiation. And then you functionalize the monomer, and then once you functionalize the monomer, you're ready to go. You can add a hydrophilic group as well to enhance the contact between the adsorbent and the sea. Then you place the adsorbent in the sea according to the scheme shown there, and the monomer and functional group grab, hopefully with a good degree of selectivity, the element that you want, and don't grab all of the other elements in seawater, because of course almost every element that's naturally occurring on the periodic table is in seawater to an extent, and so selectivity becomes a big challenge. You're selecting uranium, but also many other elements as well, most of which have no value and are just taking up sites that could be occupied by uranium. So to give another view here and to give you an idea of the scale of what would this enterprise really take if it was done at a significant scale, on the right there is an illustration of what an adsorbent field might look like. And so this is sized to produce around 1,200 tons of uranium per year, which is roughly 1/10 of annual US demand, to put it in perspective. So that is a field of adsorbent, and what you see there, those little chains on the bottom part of the illustration, are meant to indicate rows of chains, right, to which the adsorbent is moored. So that's a top-down view. Sideways view, you see at the top there, the adsorbent braids suspended upward, right, positively buoyant, spaced 8 meters apart to avoid tangling, and then the chains are spaced laterally 60 meters, also to avoid tangling. The braids themselves are 60 meters high. So that's relatively widely spaced. One of the reasons is to avoid tangling. I'll talk about another reason for that spacing as well. The footprint of that is significant. So again, because of the low concentration here, remember that the adsorbent braids themselves, and you can see an illustration of what one looks like, standing upward like kelp, and they look a lot like kelp, right? That has a mass of around 1 kilogram per meter, the material itself. So what you're talking about here for a field this size is putting several tens of thousands of tons of polymer into the ocean. It's a substantial enterprise, right? And the footprint occupied here for 1,200 tons uranium per year is around 500 square kilometers. So if you wanted to fulfill US annual uranium demand using this scheme, the footprint on the seabed would be about the size of the state of Rhode Island, right? Which in the context of Texas is nothing, right? But up here in the Northeast, you guys may think that's big. So have to get that in there. Of course, that footprint would shrink in size as the adsorbent becomes more efficient at taking up uranium, of course, right? Because we're grabbing at the moment only a few grams of uranium per kilogram of adsorbent we put under the surface of the sea. So proceeding a little bit to the technology and just getting into how this works, right? How is uranium taken up by these ligands? Well, how does uranium exist in seawater? It's a uranyl ion, in general, bound to a carbonate, right? And so it requires two of these adjacent amidoxime ligands, which essentially come and grab it, right? And the two ligands work together, and you can see there in that illustration, to grab the uranium. Unfortunately, I'll show you a table a little bit later on. They also like, and I'm saying this is the worst ligand we found except for all of the others, because they also like to grab many other elements as well, this particular ligand. So selectivity continues to be a challenge, right? And so the search for new ligands is one that's ongoing, and here the theme of my presentation is really focused on the R&D that's being done in the US, where there's a substantial effort led out of Oak Ridge National Laboratory, but also involving Pacific Northwest and Lawrence Berkeley laboratories, as well as a consortium of around a dozen universities around the country. And several of these groups are involved in ligand design, screening, and testing. And so you see the loop here. I'm not going to go into details, but the idea behind the R&D cycle, right, is to use computationally aided design studies to choose or to down-select attractive candidate ligands, synthesize the ligands, and then test them in a real seawater environment. Of course, first you test them in a laboratory environment, but there's no substitute for testing the material in real seawater because of, I'll say, the chemical composition of seawater is one thing, could be replicated in the laboratory, but biological activity, biofouling, which I'll get back to, the interplay with marine life is very significant as well. So then just proceeding to, I've already covered this, so I'll just briefly go over again, how does this radiation-induced polymerization take place? How is it so that we get the ligand to stick onto the substrate? And so there are basically 4 steps. Take the trunk polymer, whether it's high-density polyethylene or something like chitin or carbon nanotubes or acrylic. Irradiate it, graft the monomers, add the functional group, and condition it in order to remove, to deprotonate the monomer that has an extra hydrogen on, which interferes with things. So I don't want to dwell on that. I'd like to get to kind of a more systems perspective to give you insight into really how does all of this come together, considering the material, how it's deployed in the ocean, and then how it's processed, removed from the ocean in order to recover uranium. So the basic flow chart that I show here starts out at synthesis of the adsorbent, Three major steps there, which I've already covered. Deployment of the adsorbent in the ocean, and then a return of the adsorbent to the shore to elute the uranium, purify the adsorbent, regenerate it if necessary. And now vital to the success, at least at the relatively low adsorption capacities we have right now, vital to the success of this scheme from the cost standpoint is that you're able to reuse the adsorbent. So in other words, it's essential to be able to elute the uranium, recondition and recycle the adsorbent, and remove it to the ocean, return it to the ocean for as many cycles as is feasible, right? And the reason for that is that even though these adsorbents that we're manufacturing are relatively cheap, on the order of $5 per kilogram to make the adsorbent material, so that's really incredibly cheap when you think about it, right? You know, we're using inexpensive chemistry, inexpensive plastic substrates. We could potentially obtain considerably higher surface areas per unit mass by using more exotic substrates, but at the moment, the cost of obtaining a higher surface area far outstrips the capacity gain. Right? So the name of the game here is inexpensive materials. Right? But even given that we've reduced the cost of producing the adsorbent materials to the greatest extent that we can, it's still essential to recycle the material as many times as we can so that that material in which you have a substantial capital investment recovers as much uranium as possible over its life cycle. The tension there, which I'll get back to when I talk about costs a little bit more, is that the cost of mooring the adsorbent in the ocean and then recovering that adsorbent and eluting it is considerable, and you're paying that each time you're mooring the adsorbent. And so schemes for reducing that mooring cost are also important. I'll talk about a couple of those. As well as the adsorbent itself, its durability suffers each time you remove it from the ocean and you use chemicals, you use generally a weak acid or base to elute the uranium, right? And that damages the structure of the ligand. And then there's a tension or a trade-off between how much you invest in terms of doing the chemistry to regenerate the ligand versus just suffering the capacity loss and returning the material to the ocean. So I've tried to give you a big picture of some of the tensions that are going on here between optimizing the chemistry and to maximize recovery and minimizing the cost. So just to take a quick look here, here's another view of one type of adsorbent. What goes into fabricating the adsorbent? I'm not going to go through the chemicals in detail. You've got high-density polyethylene, as well as several of the chemicals that go into fabricating the amidoxime ligand. I'll skip the details there because I think that the fiber characteristics and shape are probably more interesting. So what does the final fiber look like? There's yet another illustration of the type that we're actually testing in marine environments. You see it starts off a pristine white, and then around a month later, following our marine tests, it's adsorbed a variety of compounds. The orange-brown color actually isn't from uranium, although that's also a characteristic color of uranium. So what do the fibers themselves look like on a microscopic scale? One way to enhance capacity is to increase the surface area of the fibers, right? The higher surface area you have, fiber area, per unit mass of adsorbent you put in the water, the greater surface area of water contacting with adsorbent you have, the higher the absorption capacity. So recognizing that, there are a variety of, I'll say, exotic fiber shapes that we've been looking at that have led to significant increases in capacity. And you see some of them across the bottom there, helical shapes as well as flower shapes, really getting quite high surface areas in meters squared per gram, 1 to 10 meters squared per gram. Of course, you could get much, much higher surface areas using other materials, and I'll talk about those briefly a little bit later on. Okay. So then moving on then, an important part of demonstrating the feasibility of the technology is having a realistic marine testing environment. So the marine testing work that we do is largely out of Pacific Northwest National Laboratory in the Olympic Peninsula of Washington, with some tests being done down the road from here at Woods Hole, as well as some lucky folks get to go down in the winter and do tests in Miami. That's a job I wish I had. But essentially, I'm showing you there some of the column and flume setups that we have to test the materials. These experimental campaigns are lengthy because the adsorption process, as the number I'm showing you there, 28 days, the absorption process is not a rapid one. It takes quite a bit of time for the uranium content in the adsorbent to come to equilibrium, on the order of 50 to 100 days. Right, so the experimental campaign itself is slow, in some cases frustratingly so, because we need to test the material under several elution cycles to understand how its durability is standing up. Okay, so where are we right now in terms of the adsorption capacity? I'd flashed some numbers earlier. Here, the key number that you can probably look at there is 56-day and saturation uptakes. So we're getting around 3 to 5 grams of uranium per kilogram of adsorbent. And there's a tension here also between the amount of time that you soak the adsorbent in the sea and the uranium that you take up. The longer you soak, and again, the kinetics as I show here are relatively slow. The longer you soak, the more uranium you take up, but the worse it is for the economics because the larger the overall adsorbent field you need to produce a given quantity of uranium, as well as the more biofouling activity you have. The longer you give marine life to interact with the adsorbent, the greater the negative effects on capacity. And so that's the next issue I'm going to discuss. Biofouling is, I'll say, one of the most significant obstacles facing the technology right now. We can get, I'll say, much better results in water that's been filtered with minimal bioactivity. But if you test in realistic environments, you have, I'll say, within a few hours of immersing the adsorbent in seawater, you get a formation of a biofilm, which already begins to affect our ability to take up uranium from seawater. And so you see a series of experiments we've done down there, a dark flume compared to a light flume. Really, we want to understand here to what extent is it important to deploy the adsorbent deeper outside the photic zone, right, to reduce bioactivity. And it is relatively important. You see kind of at day 42, a pretty graphical illustration of the differences in bioactivity between the light and the dark flumes. Overall, though, in environments of high bioactivity, we lose 20 to 30% of our capacity, and possibly even more than that at higher water temperatures. We've tested at 20 degrees Celsius so far. The higher the water temperature, the greater the bioactivity that's involved. So now I'd like to go on to, I've talked about what I've called the reference concept, the standing kelp fields of polymer with an amidoxime ligand. There are a variety of innovative concepts looking to address shortfalls of this reference technology, one of which is looking at novel substrates. So nanoporous carbon materials offer very, very high surface areas. You remember I quoted earlier around 1 to 10 square meters per gram surface areas for the highly structured fibers. But if you go to a nanostructured material, clearly you can get much, much higher surface areas than that. It's 10 to 100 times higher, right? So anywhere from a few hundred to several thousand square meters per gram of surface area. And this seems to be a winner at first blush. Unfortunately, the problem here is that it's difficult to capitalize on all that surface area. It's difficult to get wedded contact with that surface, right? And so, in fact, the increase in capacity we see here is marginal compared to the lower surface area fibers, and much more than offset by the extra capital cost or the extra cost with this more expensive substrate. I mean, if you start with polyacrylonitrile, it's not quite as costly. But nonetheless, this concept is one where we haven't yet figured out how to fully capitalize on the higher surface area that nanostructured materials offer. Another obstacle to large-scale deployment of this technology is if you take a step back, you realize we're talking about deploying, as I mentioned earlier, tens of thousands of kilograms of plastic to the ocean per year, right? And so think about that for a moment. Right, we already have a problem with the accrual of plastic in oceans, right? The great garbage patches, it's a pretty well-known phenomenon. And so even if we can guarantee that we recover all or essentially all of the polymer we put in the ocean, it's still a significant challenge, I'll say, to convincingly demonstrate that we're not making worse the problem of human-made debris in the oceans, right? So an obvious remedy to that is to look for biodegradable organic substrates, right? And so one substrate that's under active development is chitin, right? Shrimp shells. And so the idea there is shrimp shell makes an attractive biodegradable polymer. The problem is that shrimp shells are a little bit difficult to work with, right? You have to dissolve them in an ionic liquid at temperature, right? And then essentially to make the sort of material that you can use as a viable substrate with a high surface area, you have to electrospin, or at least this is the technology we're pursuing. This is work I'm doing with the University of Alabama. You have to electrospin the fibers, right, into a sheet, essentially a nanomat, right, that offers high surface area. And the costs here are still high because the ionic liquids that are necessary to dissolve and coagulate the chitin, it's not an easy polymer to work with, are substantial. And the substrate itself, we're back to the brittleness problem that we faced in the 80s and 90s, right, with some of the earlier substrates. And so right now, this is very promising, still in its early stages. But my personal opinion, since I'm not officially representing DOE here, even though despite the title of the slides, is that I don't think that the polymer, the plastic substrate, is going to be viable in the long run. I think that something like this will be necessary, right, to make this technology one that's really deployable. On that token, novel deployment strategies. I've spoken already about the reference strategy of suspending slightly positively buoyant strands of flexible adsorbent from the seabed. This represents, as you'll see shortly, the mooring cost represents, even though it's about as passive as one could manage to make it, represents around 30 to 40% of the life cycle cost of producing uranium from seawater. And so this is a challenge, I'll say, that's equally important to the chemistry side of the project to reduce that cost. And so again, highlighting work being done here at MIT by Alex Slocum, you look for synergies where folks are already deploying structures in the ocean, and you can piggyback on that deployment. So one synergy that Alex is looking to leverage is offshore wind farms. And so his scheme is called Wind and Uranium from Seawater Acquisition Basic Infrastructure, WASABI. He's just looking for something with a Japanese theme for his acronym. I think it's pretty cute. Right, and the scheme there, as you can see on the lower right, is to suspend these braids. It's not to scale. There's around 100-meter vertical change from the top of the offshore wind turbine to the bottom of, or 50 meters, I'll say, to the bottom of the adsorbent bed, right, is you have very slowly circulating on a very slow conveyor strands of this polymer adsorbent, which are over the course of 50 days, right, take their turn being dunked in the ocean, come back up, and then the little tanks on the top are meant to illustrate chemical processing, right? So the elution of the uranium takes place on site, right, on each wind turbine, and the parasitic power consumption is tiny, right? So in other words, you take a tiny share of the electricity produced by the wind turbine in order to drive the elution system, which has relatively low energy requirements. So the operating costs here are reduced to occasional servicing of these facilities by a workboat, or maybe you connect them all by pipeline to the shore and it's almost fully remote. Right? So this is one of a few innovative schemes for reducing the deployment cost. And again, the idea is to capitalize on synergies where folks are already, to produce other commodities, already taking significant masses out into the ocean and mooring them somewhere. Right? Okay. Whoop. So I just hop forward a couple of slides there. So now moving on to activities in other countries. I've already spoken about the Japanese. These are a couple of slides that I've taken from the Chinese Academy of Sciences. And so the Chinese have a relatively new and very robust program. What they're focusing on is not so much ligand development, but scale up to industrial scales. And so they're looking at fabricating on a continuous basis large quantities of adsorbent using accelerator irradiations. And they're also looking at mooring significant quantities. You see one of their deployment sites there, mooring significant quantities of this material off the coast of China to demonstrate the entire life cycle from large-scale production to large-scale mooring, elution, and recovery. And this is really, I'll say, an outstanding complement to the US program, because while we're doing small-scale testing, which I've shown you some illustrations, the US has no plans to do large-scale manufacture or deployment of the adsorbent. So it's really an excellent synergy with the Chinese program. Okay, so now in the last few minutes, I'll briefly talk about costs. Where do we stand? What are the major cost drivers? So here are some key numbers that I'm going to use to describe sensitivities, highest leverage parameters to affecting the cost of uranium production. I've already talked about uranium uptake in grams uranium per kilogram adsorbent. How long do you leave the material in the ocean? Optimal is around 50 to 80 days. How often do you recycle the material? Optimal is 6 to 14, and the tension there again is how quickly does the material degrade when you recycle it. Water temperature is an interesting one. The higher the temperature, the better the adsorption, but also the higher the temperature, the more the bioactivity. So it really depends on the degree of light at a particular site. as well as the degree of dissolved oxygen, right, or hypoxic area or not, right? So it's highly site-specific as well. Again, biofouling here, I'm showing a range of 0 to 20%, again, depending on those parameters. Okay. So where did we stand when the US campaign began? The first materials we were testing, the uranium production cost associated with that, we estimated at around $1,200 per kilogram uranium. Now we're down to around half that level, and I'm quoting there $500 to $900 per kilogram uranium. Higher capacity, significantly higher capacity, double to a little bit more than double. Some loss in durability compared to where we started. One of the major design tensions that we're facing is that these high surface area fibers with the helical and other structures are also more vulnerable to being damaged when the uranium is eluted from them, right, during recycling of the adsorbent. So trying to give you an idea of some of the sensitivities here. Here I'm plotting uranium production cost versus number of times the adsorbent is reused. And so you see this curve flattening out, right? And the reason it doesn't continue to descend, that there is an optimal number of reuses, is because you're losing capacity each time you recycle. And the shape of these curves depends on that capacity loss. At some point you stop, you throw away or recycle the material, the adsorbent material. It's polymer, so it has scrap value. And you start over with fresh adsorbent because the incremental cost of deploying the adsorbent again, right, to the ocean with reduced capacity is greater than the benefit that you'll get from the reduced amount of uranium that you're recovering. And so what you can see here is some idea of where we would need to head with the current adsorbent technology in order to be competitive. Right now, the darkest blue curve, around 4 grams uranium per kilogram adsorbent, is where we are now. If we could, I'll say, nearly quadruple that to 15 grams uranium per kilogram adsorbent and keep durability about the same, we would be at around $200 per kilogram uranium, which, not competitive with today's market prices, but arguably if that could be achieved, and it could be achieved convincingly, one fulfills this purpose of establishing a backstopping price that's reasonable, not out of line with current uranium market prices. So this just shows how that picture changes as you change the capacity loss per recycle. The green wedge there, or no, I'll say the purple wedge, the mooring and deployment wedge is an interesting one because that purple wedge doesn't get smaller as you continue to increase the number of uses of the adsorbent. So mooring and deployment, as well as the back-end costs, they take a progressively larger share of the overall uranium production cost as you use the adsorbent, reuse the adsorbent more times. Right? Because the more frequently you can reuse the adsorbent, the more uranium you're recovering, and so the smaller the capital cost per unit of uranium you've recovered. Each mass of adsorbent recovers more uranium over its life cycle. But the cost of deployment is constant per reuse. So that wedge, not getting smaller, really establishes a minimum cost for the production of uranium from seawater, right? At least at that capacity. So in other words, unless we think of a more clever way to deploy the adsorbent to the ocean and return it, the cost here is not really, holding chemistry fixed, is not really going to go below around $300 to $400 per kilogram uranium. So that's why thinking about clever deployment schemes is equally significant to considering the chemistry. So length of campaign, it would be desirable to go to a shorter campaign. We could have a smaller overall adsorbent field, but it simply takes the adsorbent right now. The kinetics are relatively slow because the concentration is low. It takes the adsorbent too long to absorb uranium. So the optimal campaign length is, as I said, around 50 to 80 days. So then just briefly summarizing, what are the cost components? What are the highest leverage components of this overall on the order of $500 to $800 per kilogram uranium production cost? Well, it's about equally split between producing the adsorbent, and you see the top row in the table there, and mooring and deployment of the adsorbent. The largest single component is the operating costs associated with producing the adsorbent, and that's mostly chemicals involved with creating and functionalizing the ligands that are used to adsorb uranium. Overall, there's a number that I mentioned below. The cost of fabricating the adsorbent, nonetheless, is remarkably low. $5 per kilogram of this functionalized plastic that we're putting in the ocean, right? And so that's been the watchword throughout, is minimizing costs because we recover so little uranium per kilogram. Okay, so then summarizing some of the significant cost drivers, I have a little chart here that shows, as a function of the number of uses of the adsorbent, the uranium production cost. Well, if we make some changes, that's a change to chemistry, changing the conditioning of the adsorbent. I don't want to get into details. If biofouling is significant at the 15% level, the uranium production cost goes up by on the order of 10%. You can compensate by shortening the soaking campaign. If we could make the material more durable, we have a significant benefit, because then there's really no obstacle to continuing to recycle the adsorbent, and this production cost drifts downward until you get to a minimum really established by what's the cost per kilogram adsorbent of taking it to the ocean, mooring it, and recovering it. Increasing the water temperature is also a significant benefit, assuming that biofouling is held fixed at its 20 degrees Celsius level, simply because of the capacity benefit. So what that means is that the optimal sites for deploying this technology are those with high water temperature and low bioactivity. Okay, so I'm getting close to the end here. I have a frequently asked questions page, some questions that frequently come up when I discuss this. First, if you put a large adsorbent field underwater, think back to the standing kelp concept, it's been asked, what's the hydrodynamic effect on that? Can you actually change or modify undersea flows by putting that much material? You're dissipating a lot of energy, potentially, right, by doing this. And in fact, that's a question that originated from Pete Lyons, previous Assistant Secretary for Nuclear Energy. So we did a set of CFD calculations that showed that really at the spacing that we were talking about of the adsorbent field, there's no more than a 10% reduction in current speed in any part of the field, and significantly less than that in terms of total mass flow downstream of the field. And there's a relatively low mooring density of the braids. The perturbation to the local ocean currents is actually significantly larger in the vicinity of existing offshore kelp fields today, right, some of which exist off the coast of California and elsewhere. Right. A couple of other questions on my FAQ. So as I've said, high ocean temperatures are beneficial, right? And if we could find a substance that had a higher concentration of salts, and as well as uranium, that would be beneficial too. So why not make use of desalination brine, right, which is both hot, elevated temperature, and enriched in uranium and all the other elements contained in seawater? Well, we could, and that would be attractive, and it's been looked at, and you recover significantly more uranium per massive adsorbent in that environment. But if you look at global desalination capacity around the world, it's 80 million cubic meters per day of fresh water. And at a typical volume ratio of fresh to seawater, that's only around 90 tons of uranium per year is going through all the desalination plants in the world, right? So it gives you an idea of the scope of the amount of water that we need to pass by these braids in order to recover an appreciable amount of uranium, right? That's why we're occupying hundreds of square kilometers of seabed, right, in order to do this. So similarly, another suggestion, why not use coastal power plants? Make use of cooling water, right? Elevated temperature, 40 C, right? And that is a good idea. But just take a typical nuclear power plant, the 2,000 megawatt units, discharge rate 45 cubic meters, that number has the wrong units, it looks like, per day. But anyway, the calculation is valid. Even if all the uranium in that cooling water were captured, right, it would only be around 3 tons of uranium per year. So considering all of the outlet of power plants on the coast, annual output around the world, nuclear and otherwise, again, it's small compared to world annual uranium demand, right? And so really the scale of this enterprise is something that you kind of have to let soak in, so to speak, right, if this is going to be done on a large scale. So summarizing the path forward, where are we now? Well, where we started from, at least in the US, is this was our best understanding of the cost of producing uranium from seawater. Where we are now, and where are we headed? Well, if we could operate in 30 degrees Celsius water, which we hesitate to take credit for because of the higher bioactivity, but if we could do that without increasing biofouling, that alone is a 50% cost reduction. Right? So we're investigating various ways of doping the adsorbent material with copper, right, with other compounds that are that impede the growth of marine life on the adsorbent. Of course, that has its own costs. Right? Near-term target, 20% capacity increase with reduced degradation. And then where are we aiming to go in the long term? Well, you see the uranium spot market price range over the past decade down there at the bottom. The potential goals, really, there are two paths forward, right? A multi-use adsorbent, I'd mentioned this earlier, right? If we want to have an adsorbent that has similar capacity to what we have been developing today, so on the order of 4 grams uranium per kilogram adsorbent, that is not going to do it even if we could reuse the adsorbent an infinite number of times. So we have to double the capacity at the very least in order for a multi-use adsorbent to, let's say, be of interest in the high range of the uranium spot market price. A single-use material, that's another path forward. So punt on trying to overcome the durability challenges of the adsorbent. And again, look at what sort of material, even if it turns to mush, as some of them do after you soak them in seawater once, right, what sort of uranium uptake would you need for a single-use material to be compelling? And for that to be compelling, we would need to increase the capacity of the material by 5 to 10 times. 6-fold is given there as an average. So those are essentially the challenges before us, and us, I mean here the global community that's confronting this. Either double the capacity of our best available materials and make them much more durable, or increase the capacity of our best available materials by a factor of 5 or 10, as well as solve challenges with deploying large amounts of plastic to the ocean, right? And comes to grips with the fact that this is a very large enterprise, right? Occupying potentially several hundreds of square kilometers, right? To produce a considerable amount of uranium. So with that, I think I'll just leave the conclusions up there. I'm happy to wrap up at this point and take questions. So.
Erich, great overview. We have definitely time for questions.
If anybody dares.
Hey, Scott. My name is Kishore. I'm a PhD student in mechanical engineering studying desalination. How could this be extended to mining other minerals? For example, you had that plot where there was lithium on it. There was
yeah, it's a fun plot.
Yeah. Like, how much of this can be transferred to general seawater mining? For example, lithium, I think, is the next, highest concentration out there, which has not been extracted.
The problem, if you move down here, right, to lower price and higher concentration,
yeah.
right, is that then, for let's say something like lithium, it will probably never be viable, except in the most passive schemes, because the unit value of lithium is so low that the amounts you need to collect per unit mass of adsorbent, simply the cost of hauling that material right out of the ocean and back to shore would probably be prohibitive. As it is right now, that's on the edge of a significant challenge for uranium. So really, I should draw another line here that says you need to look upward also. The highest value materials, right, reduce your unit operations cost per unit value of product. Does that make sense?
Yeah.
So. I should say that there are other commodities, other elements are being recovered from seawater. Vanadium has been recovered on small scale. I didn't really get into vanadium here. It's sort of a pest more than anything. Vanadium has, I'll say, just as much affinity for this ligand as uranium, and the stuff doesn't want to come off. So we can't elute the vanadium, remove it from the adsorbent without destroying the adsorbent using a stronger acid, which then reduces our recyclability. So that's just one of many technical challenges under here that I didn't get into.
It was very related. I was just wondering if there's any chance for co-production to bring down the cost of uranium.
Excellent question, right? And so I didn't get into that in this talk. Vanadium, again, it's kind of a two-faced commodity because we do recover significant amounts of vanadium, which is just on the edge of being interesting as a co-product. The problem is we have to make the decision, is it worth it to get the vanadium off? Or do we wait until the end when we're going to trash the adsorbent anyway? It's already long since reached its saturation capacity. At the moment, it looks like it's not worth it to take the vanadium off. For the adsorbent, I wish I had a table of the affinities of our adsorbent for different elements. At the moment, nothing else is really competitive, right, as a co-product. We've looked at some of the precious metals. Our ligand just doesn't have an affinity for that. So the short answer is we're looking at it, but nothing has jumped out yet.
Is there any variation by isotope for uranium from seawater?
That's a good question. And there is a small variation. I'm trying to remember here the reasons. The U-234 in seawater is slightly enriched, I think. And that's because of, because of the mechanism for deposition of uranium in seawater, the way it's mobilized from the surface, right? And so uranium, It's because of the differing solubilities between uranium and thorium, right? Uranium is soluble, thorium is really not. So uranium-238 decays to thorium-234, which then will beta decay a couple times to U-234. So the thorium is not mobile, but the uranium is. So that's where you get actually the uranium enrichment. The U-234 gets transported in preference to the thorium.
But I think he had in mind a juicier isotope than 234.
But that's the only one for which there's an appreciable difference, to my knowledge. It's just kind of fun more than anything because it doesn't have a it's not enough to really have a practical effect.
I assume the quoted price of conventionally obtained uranium doesn't include a lot of externalities that people worry about, like mining remediation, social disruption, landscape destruction, and so on. It also sounds like the methods you're describing have relatively few externalities associated with it.
You know, that's an excellent point, and one that I could have gone into, but I didn't want to offend any in the mining industry in the audience, right? So I think that, you know, if you look at, it's not just uranium. I don't want to single out uranium because many, especially of the heavy metals, face the same challenges around the world. Some provinces in Australia have mining bans. Australian territories have uranium mining bans in effect. The costs of remediating uranium mines in the US, in Australia, elsewhere, have been very substantial, adding, you know, tens of dollars per kilogram uranium to the production cost. And so currently, I think the regulatory environment is such that, you know, mines can only open and operate if they have a approved plan for remediation and shut down afterward. It remains to be seen how robust all those will be. But in my opinion, one of the major drivers here, right, possibly toward this technology is just what you'd said. If this technology can overcome its own environmental challenges, which I'll say are substantial, another I didn't get into was the fact that, you know that biofouling I talked about, right, accretion of organisms on the adsorbent. Unfortunately, marine life sees that as a tasty snack, right? And so what tends to happen is that marine life, larger life, macroscopic life, will eat, right, the adsorbent, which number one reduces adsorbent, the quantity of adsorbent, not substantially, but a little bit. Number two, though, integrates a material that concentrates heavy metals into the food chain. That's right. So, but that having been said, I believe that the challenges, if you can find an environmentally appealing substrate, and if you can, I'll say, reduce the bioactivity of the fibers, I think those are solvable challenges, right? I think that the environmental footprint of this technology has the potential to be a lot more benign, right, than conventional uranium mining and milling. So I agree with you.
Please. It wasn't clear the difference between the Chinese large-scale method and what you're doing at a small scale.
Oh, okay, there's no difference really, except that the Chinese haven't, at least not yet, really gotten into the business of designing sophisticated ligands, right? What the Chinese are primarily focusing on is taking the off-the-shelf technology developed in Japan and now improved in the US, and looking at how that technology scales up if you were going to fabricate it at large scale, right, and then deploy it in the ocean at large scale. So they're really much more on the engineering side. How do we build a whole bunch of this stuff cheaply and deploy it in the ocean cheaply? Does that make sense? Yeah.
I'm going to ask one. If the challenge is deployment, the cost of deployment and recovery, has anyone been thinking about using the current fleet of large container ships flying back and forth?
Funny you should mention that.
Yeah,
So.
Because you already have an infrastructure at both
You
sides
do,
of the
and
Pacific.
so that's exactly what I was speaking about when I was saying, look at existing mechanisms for deploying large amounts of material to the ocean. And so we have a concept that we advanced to an early stage of essentially attaching the adsorbent material as, think of hairnets, right? Gigantic hairnets that you fit on the bottom of a ship, right? The problem with that, though, and again, what this all founders on is how little uranium you recover per unit mass, right? That we haven't done detailed CFD yet, but I don't think we have a reason to, because our scoping calculations have shown that the extra mass and the extra drag, the fuel costs associated with that, more than offset the amount of uranium we recover. So we looked at it, we were excited for a while, and then we went, oh. So.
All right, very good. So let's thank our speaker one more time. Thank you.